Okay, so this is the introduction. Our project explores energy harvesting and fitness trackers, focusing on durability, convenience, and environmental benefits. We aim to create kinetic-powered smartwatches, transforming movement into electricity for continuous operation without traditional charging, minimizing battery waste, and promoting sustainable technology. It's important so that we can help reduce like the battery cost and overall waste of like the resources we have on Earth. This approach is also supported by recent studies, including the MDPI's kinetic energy logger research, demonstrating the feasibility and ecological potential of such wearable devices.
Current fitness trackers often need frequent recharging, disrupting the user experience and limiting usefulness during activities like long hikes. This highlights the necessity for trackers with extended battery life to improve convenience and longevity. Additionally, the reliance on conventional batteries in wearables leads to significant electronic waste and environmental harm, emphasizing the need for a shift to sustainable power sources to reduce the ecological impact.
Hello, Professor. My name is Daniel Guzman. I'm going to provide a brief summary of the background and related work of our little research project regarding the energy harvesting using piezoelectric materials for a wearable device. Before, there were other studies using other types of energy harvesting sources. You have kinetic harvesting, basically movement, electromagnetic, using the electromagnetic field of the body, electrostatic, using the static electricity created by our body, and triboelectric technologies, which means the use of a tourbillon or other method of generator in order to generate electricity, mechanically generate electricity, so spinning something basically. One of the main problems regarding these methods is that the fact if they require a custom generator or a custom built piece of hardware that needs to be produced in order for the design to be valid or efficient, it increases the cost uh, very significantly. Um, Also, there were other studies done related the optimal placement of and how many of these piezoelectric devices in order for the optimal production of energy, especially doing different type of activities like cycling, running, uh, and how actually to distribute the load of that you are taking out of these piezoelectric devices, because the current that is produced by this device is very small, usually in the microampere range, and the voltage is substantially higher, which means that they're high impedance source. So you need to be careful when you are measuring or doing any type of loading of these devices, because you may actually, by measuring the voltage that you're producing, may actually discharge or use part of that energy that you're generating.
Continuing with the environmental impact, the potential for these devices that can generate electricity for the battery is pretty great. As like that would help to greatly reduce the natural resources we use for them, because this would allow you to make them smaller, or you can, in conjunction, you could also not have to replace them as often. This would in turn reduces the amount of natural resources you use, but also allows you to like uh, expand, like get more out of the resources you have in a sense. So you can create more batteries and more um, devices out of the material out of the materials you saved. This also would allow you to not have to charge at home, which would also reduce like other natural resources like copper, as you won't have to have a separate charging cable to charge the smartwatch anymore. Um, another way that we can reduce the environmental impact is by having better integration within the smart devices. Having placing like the charging mechanism within the smartwatch itself is a key way. If we can make it small enough, is a key way to help reduce the impact. As it's smaller, it will use less material and it can be more tightly integrated, or even integrated it into the band of the watch itself is another way that we can in, uh, integrate it, and so that we can save on resources. And as a whole, the for the design of the watch, using more sustainable materials and also materials that are more durable and that can be more easily recycled is also like a very important key way that we can make these devices more sustainable as a whole.
Here we explore the seamless integration of technology in our wearables, combining energy harvesting, circuit management, and data logging for optimal performance validated by rigorous system evaluation. At the heart of this system is a compact piezoelectric generator, or PEH, manufactured by MIDE. This particular generator was selected for its compatibility with wearable technologies. One innovative feature of the PEH is its tunable resonance frequency, which we synchronize with the frequency of human activities using neodymium magnets. The images labeled A and B lay out the circuit for this energy harvesting setup. They depict the journey of the energy from the PEH through critical components, like the rectifier and battery charging integrated circuit, ultimately feeding into a low power Bluetooth capable microcontroller unit. These components collectively facilitate the transformation of kinetic movement into usable electrical power. Moving on to slide 9, we delve into the intricacies of circuit management. The aim here is the efficient conversion of the harvested AC current to DC, optimized for charging the device's battery. Central to this process is an ultra low power microcontroller with Bluetooth capabilities, responsible for logging energy data. The strategic selection of components, along with firmware optimization that minimizes energy consumption, is important to the design philosophy. These considerations are crucial for ensuring that the device can efficiently harness kinetic energy, leading to a reliable and eco friendly wearable experience. On slide 10, we focus on the data logging aspect of the system. The microcontroller unit in question is part of the RFD 771001 module, incorporated into the LilyPad assembly board, which is purpose-built for wearable applications. Featuring a BLE radio and an ARM Cortex processor, the MCU precisely measures the voltage and current from the PEH, relaying this information to a mobile application via Bluetooth. This function provides us with valuable data on energy harvesting efficiency and allows us to understand the charging current dynamics during various user activities. Slide 11 showcases the practical evaluation of the PEH system. They conducted tests involving 10 participants who engaged in physical activities like jogging, documented in figures 6 and 7. We can see energy transfers to battery amounting to 1.75 millijoules to 2.98 millijoules per activity, which is a significant step towards self-sustaining wearables. This translates to an operational time extension of several seconds for the battery after each activity.
Hello, Professor. This is Nathaniel Guzman, and I'm here to provide a little quick conclusion for our presentation. So, wearable devices are just going to keep expanding in functionality uh, as the IoT and other technologies are added into these devices, and the adoption is greater and greater. Well, the only thing that we expect is that the pace of the increase of the consumption of these devices is going to be as high or even greater than when it was like with the phones or the smartphones were being produced by the first time. We're seeing that I believe, especially that there's going to be a switch between the use of the phone and instead towards the use of a wearable device. I'll most likely we will not be using phones in a very for a very long time as we thought we would, because again we already have wearables in which we can see pictures on them, we can record audio, send messages. So all these devices are just going to increase in functionality. Also, they're going to increase in size, and they're going to increase in the time that we're wearing them. Thus, it's very important that we manage the importance of how we're going to charge these devices, how we're going to produce power for these devices, because we cannot depend only on these devices having a larger battery, a larger battery, a larger battery every single iteration, like we have seen currently in the market. We need to definitely provide solutions, which is what we're trying to do to solve this problem of getting the battery just simply getting bigger to every iteration. One of our solutions, the one that we propose, piezoelectric generators produce a significant increase in battery duration if they are used compounding their effects. Basically, on our study, the gain was about 3.6 seconds to about 6.2 seconds, and basically doing the everyday activities that we all do, jogging, walking, standing around. Especially in my case, in my job, I walk 2 miles every day. So this type of addition to the charging system of a wearable device like my smartwatch will definitely increase the amount of time that I will have to spend without charging it. And it's actually, in my case, I have an Apple Watch as an example. It is very sometimes troublesome because you have to either charge your phone or your Apple Watch. You only have one charger. So this type of technologies will allow you to like stop doing that, or maybe keep the device on you all the time without taking it out, which will produce also increase improvements in, it's like example, people that have to track their sleep and other activities that you have to have the watch on every day, pressure blood pressure monitoring, in which you really don't shouldn't um, remove the device out of your hand, in example. I hope you like our presentation. Have a good day.